At the end of this video, you should be able to describe the interaction between two objects in terms of the change in momentum of each object, compare the total momentum of two objects before and after they interact, state the law of conservation of momentum, and predict the final velocities of objects after collisions, given the initial velocities, force, and time. Chapter 6, Section 2, Conservation of Momentum. Momentum conservation. So far in this chapter, we have considered the momentum of only one object at a time. Now, we will consider the momentum of two or more objects interacting with each other. Figure 2.1, which is shown on the screen here, shows a stationary billiard ball set into motion by a collision with a moving billiard ball. Assume that both balls are on a smooth table and that neither ball rotates before or after the collision. Before the collision, the momentum of ball B is equal to 0 because the ball is stationary. During the collision, ball B gains momentum while ball A loses momentum. The momentum that ball A loses is exactly equal to the momentum that ball B gains. Figure 2.2 on the bottom of your screen here shows the velocity and momentum of each billiard ball both before and after the collision. The momentum of each ball changes due to the collision, but the total momentum of both the balls remain constant. In other words, the momentum of ball A plus the momentum of ball B before the collision is equal to the momentum of ball A plus the momentum of ball B after the collision. This relationship is true for all interactions between isolated objects and is known as the law of conservation of momentum. For an isolated system, the law of conservation of momentum can be stated as follows. The total momentum of all objects interacting with one another remains constant, regardless of the nature of the forces between the objects. Momentum is conserved in collisions. In the billiard ball example, we found that the momentum of ball A does not remain constant, and the momentum of ball B does not remain constant. But the total momentum of ball A and ball B does remain constant. In general, the total momentum remains constant for a system of objects that interact with one another. In this case, in which the table is assumed to be frictionless, the billiard balls are the only two objects interacting. If a third object exerted a force on either ball A or ball B during the collision, the total momentum of ball A, ball B, and the third object would remain constant. In this course, most conservation of momentum problems deal with only two isolated objects. However, when you use conservation of momentum to solve a problem or investigate a situation, it is important to include all objects that are involved in the interaction. Frictional forces, such as the frictional force between the billiard balls and the table, will be disregarded in most conservation of momentum problems in this course. Momentum is conserved for objects pushing away from each other. Another example of conservation of momentum occurs when two or more interacting objects that initially have no momentum begin moving away from each other. Imagine that you initially stand at rest and then jump up, leaving the ground with a velocity v. Obviously, your momentum is not conserved. Before the jump, it was 0 and became m times v as you began to rise. However, the total momentum remains constant if you include Earth in your analysis. The total momentum for you and Earth remains constant. If your momentum after your jump is 60 kilogram meters per second upward, then Earth must have a corresponding momentum of 60 kilogram meters per second downward, because total momentum is conserved. However, because Earth has an enormous mass, something like 6 times 10 to the 24th kilograms, its change in momentum corresponds to a tiny velocity change, something like 1 times 10 to the negative 23rd meters per second. Imagine two skaters pushing away from each other, as is shown on the screen here. The skaters are both initially at rest with a momentum of 0, meaning the initial momentum of person 1 is equal to the initial momentum of person 2, both being equal to 0. When they push away from each other, they move in opposite directions with equal but opposite momentum, so that the total final momentum is also 0, meaning the final momentum of person 1 plus the final momentum of person 2 is equal to 0. At this point, you should be able to understand sample problem D.
In the absence of friction or any other external forces, the total momentum of a system of objects interacting with one another remains constant, regardless of the nature of the forces between the objects. When two skaters, originally at rest, push each other away, in the absence of friction there are only internal forces acting on them, so the total momentum of the two is conserved. As they move apart, the skaters have momentum that is equal in magnitude but opposite in direction. Therefore, their momentum has opposite sign and the total momentum is equal to 0, just as when they were at rest.
Newton's third law leads to conservation of momentum. Consider two isolated bumper cars, M1 and M2, before and after they collide. Before the collision, the velocities of the two bumper cars are represented as v initial 1 and v initial 2, respectively. After the collision, their velocities are vf1 final and v final 2. The impulse momentum theorem, force times delta t is equal to delta p, describes the change in momentum of one of the bumper cars. Applied to M1, the impulse momentum theorem gives the following. Force 1, delta t, is equal to M1 v final 1 minus M1 v initial 1. Likewise, for M2, it gives the following. Force 2, delta t, is equal to M2 v final 2 minus M2 v initial 2. F1 is the force that M2 exerts on M1 during the collision, and F2 is the force that M1 exerts on M2 during the collision. Because the only forces acting in the collision are the forces the two bumper cars exert on each other, Newton's third law tells us that the force on M1 is equal to and opposite the force on M2, which is to say, force 1 is equal to negative force 2. Initially, the two forces act over the same time interval, delta t. Therefore, the force M2 exerts on M1 multiplied by the time interval is equal to the force M1 exerts on M2 multiplied by the time interval, or F1 delta t is equal to negative F2 delta t. That is, the impulse on M1 is equal to and opposite the impulse on M2. This relationship is true in every collision or interaction between two isolated objects. The image on the screen here illustrates the forces acting on each bumper car. Because impulse is equal to the change in momentum, the impulse on M1 is equal to and opposite the impulse on M2. The change in momentum of M1 is equal to and opposite the change in momentum of M2. This means that in every interaction between two isolated objects, the change in momentum of the first object is equal to and opposite the change in momentum of the second object. In equation form, this is expressed by the following equation. M1 v1 final minus M1 v initial is equal to the negative quantity of M2 v2 final minus M2 v2 final, initial. This equation means that if the momentum of one object increases after a collision, then the momentum of the other object in the situation must decrease by an equal amount. Rearranging this equation gives the following equation for the conservation of momentum. M1 v1 initial plus M2 v2 initial is equal to m1 v1 final plus m2 v2 final. Forces in real collisions are not constant during the collisions. In this course, the forces involved in a collision are treated as though they are constant. In a real collision, however, the forces may vary in time in a complicated way. The image on the screen here shows the forces acting during the collision of the two bumper cars. At all times of the collision, the forces on the two cars at any instant during the collision are equal in magnitude and opposite in direction. However, the magnitudes of the forces change throughout the collision, increasing, reaching a maximum, and then decreasing. When solving impulse problems, you should use the average force over the time of the collision as the value for force. Recall that the average velocity of an object undergoing a constant acceleration is equal to the constant velocity required for the object to travel the same displacement in the same time interval. The time-averaged force during a collision is equal to the constant force required to cause the same change in momentum as the real changing force. At this point, you should be able to describe the interaction between two objects in terms of the change in momentum of each object, compare the total momentum of two objects before and after they interact, state the law of conservation of momentum, and predict the final velocities of objects after collisions given the initial velocities, force, and time.